Irena. Good morning, everybody. And the presentation changed the title during last days. And also the content of the presentation changed day by day, because from the day when Nicola wrote me, oh, Max, could you present something at this PTS? We have a free slot. And I was very excited because we had a very interesting experiment of our new robot with citizens' involvement and so on. So I said, okay, I can present it. But then it basically pushed myself to rewind in some way what we made in our lab during last 3 years, and to look for following the lines that connected what we developed in robotics research, technology development, innovation, and experiences with end users, both scientific and industrial. And so we can start from what I presented here 3 years ago, when we started from operational needs of portable, modular, unmanned marine vehicles, both ROVs, unmanned semi-submersible vehicles, surface vehicles, and so on, and the challenge of designing and developing a family of unmanned marine vehicles based on robotics bricks that can be combined at field to configure different systems. And the result was what at that time for us was the pop-art concept, that is a polar portable autonomous robotic technologies. Polar because it was in some way motivated by some polar application. So we could move from a specific operational needs to a more generic concept of a vehicle that started as an ROV, a torpedo-like ROV, and open frame where you can change and mount different devices. And you can upgrade it, removing the cable, putting batteries on the bottom, and communications on the top, acoustic modem, you have an AUV. But if you put on the top GPS and Wi-Fi, you have a semi-submersible vehicle, and combining two of them, you can have a catamaran. That was this basic idea, and then we started in the last 3 years to exploit that. And at first we demonstrated and we saw that it is possible to move from ROV to semi-submersible configuration in a very easy way. For instance, this is in the beach in New Orleans and in Svalbard. It is possible to do that on the deck of a ship. And the main idea is that you can go at sea with only one vehicle, and you can easily reconfigure it manually to operate it underwater and on the surface. As you can see here, you can add the battery pack to the ROV after, and then you can remove the cable, turn the vehicle, unplug the optical fiber, moving the vertical thrusters, because when you are on the surface, so you move thrusters from vertical to horizontal position in order to have more thrust, and then you can mount the upper part and you reconfigure the vehicle. This operation was 10 minutes, something like that. And then the vehicle was exploited in this configuration in different projects. One in 2017 was a CNR self-funded project in Svalbard Island in New Orleans, where CNR manages dirigible Italian station. And the idea was to sample water and environment very close to the walls of the glacier tongues, and to study interface between ice, water, and air. And in that case, we operated both semi-submersible and air vehicles to understand how it's possible to work with them together. And we have some images of the environment of the vehicle navigating close to the wall surface, and the air vehicles taking infrared images of the sea surface, and also samples with multiparametric gauge of the column of the air. You have the vehicle reaching the glacier, and an idea of which is the conditions. It is very dangerous to go there. To sample that area is very important to understand the dynamics both of ocean and of atmosphere, but you cannot go there with manned systems because it is too dangerous. The ice wall is 50 meters high, and it is continuously breaking. And 1 year later, we went there with a training in the framework of the Excellabus project coordinated by Nicola, and researchers from Zagreb, Limerick, and Girona could have a short taste of what happens there. And in that case, okay, we tested a different concept of sampling the air and water column in the proximity of ice walls, because to have more unmanned vehicles in water and in the air from a very small support vessel is too complex. So in that case, there were mounted 2 winches on the vehicle, one for a balloon with an atmospheric multiparametric gauge, and the other one with a CTD attached. So in that case, we were able to manage to sample a column of 50 meters in the air and 50 meters in the water, upper and below the vehicle. And also we mounted simple water samplers on the side of the vehicle itself. So you see what happened in this case, and you have a balloon also taking measurements of the atmospheric parameters. And you see here the vehicle from the balloon, and this can give you the idea of which is the environment in that place. And we are in this case 79 degrees north in Svalbard. But when you have this kind of technology, you can reconfigure the vehicle. So it is funny because when we thought that, we were saying, okay, we started with this clockwise arrows. We have underwater ROVs, then autonomous underwater vehicle, and then semi-submersible. But the project that funded this were on counterclockwise direction. Then currently we have the MATRAC ACP project. This is a project for having AUVs for adapting sampling of harbor waters. This is in Interreg Maritime Italy-France. Other partners are University of Genova and IFREMER. And in that case, we plan to use an AUV for collecting samples for monitoring the waters in harbors. But there are some problems. Some problems are legal, because in Italy you cannot operate this vehicle in the harbor of Genova if you have not a physical connection to the support ship. And so in that case, we opted for a small Dyneema connection. And the other is more technical and logistic, because in order to have accurate positioning of the vehicle underwater. So since we work in less than about maximum 12 meters of water, the idea is to have a buoy that is mounted on the top of the vehicle, connected with a cable. We can keep the length of the cable almost equal to the depth of the vehicle in order to have the buoy just on the top of the vehicle. And so we can have a GPS and a Wi-Fi connection directly to the vehicle underwater. And now we are designing this main small winch with cable. We are adapting a small winch for mini ROVs and so on. So this is basically the idea. And in some sections of Proteus, we can mount the special devices for this project. So this will be an AUV mode in some way. And another way is the Ares project. This is an Italian-funded project, a big project with a budget of 10 million. It is starting now. There are all the problems related to national projects that we discussed this morning during breakfast with Zoran. And in this case, the idea is to make a step forward the autonomous ship, having a manned extended ship. So the idea is to have a ship that is usually a ship used for monitoring of hydrographic monitoring and so on. And it is a manned ship, and it will be extended with AUVs and ASVs. And in that case, the AUV will be Proteus in a more, there is also budget for making research on improving its hydrodynamics and so on. Then we have a project that many of the people here are involved, and it is human robots. And the Proteus will be one of the infrastructure available in the upcoming third TNA call of human robots, and in particular, having the opportunity of the dirigible Italian station. In this call, Proteus will be linked to the possibility of exploiting it and making research in the dirigible Italian station. So this will be in the third call that will be published in these days, and it will be possible to mount sensors, devices, what you like, on Proteus, and due to the duration of the project and logistics that we have to prepare, the campaign is foreseen for next September. And then, okay, with the project that is going to start on December 1st, we are moving back to ROV mode of Proteus. And this is Bluehouse, Blue Robotics for Sustainable Eco-Friendly Services for Innovative Marinas and Leisure Boats. And probably we have to discuss a lot about Fabio for capitalization of this project and some of the projects that you mentioned. And Antonio Pasquale is partner of this, and also there is the Navigo cluster of Tuscany, and Aninver, that is a Spanish company working on business organization, and OptionsNet, that is a Greek company, software company, developing apps for marinas. And in this case, the idea is to extend the marinas to coastal areas, allowing people to explore underwater sites in protected areas, for instance, directly piloting the ROV from a room in the marina, or also the idea, one of the business possibilities that we have to explore. Vincenzo Poerio, the former CEO of Benetti, is in the advisory board, is to understand if it will be possible and reasonable to include an ROV in the domotic of luxury yachts and other things of this. There will be two sites, one in Viareggio and one in Algarve for this. And so this is basically what we made with Proteus. But a couple of years ago, we had other operational needs that were basically related to develop a portable and modular unmanned surface vehicle for ultra-shallow water applications. And for ultra-shallow water, what I mean for that is less than half a meter. And the request was for a low size, that means transportable in a car trunk, and low weight, that is operable by two people. So the challenge in this case was the same of the one that we had with Proteus, but in this case, the need was only for unmanned surface vehicles, not for a reconfigurable transformer able to work underwater on the surface and so on. But thinking about that, with the previous experience of Proteus and Pop Art, we arrived to a new concept that is in some way inspired and goes beyond the Morph project that many of you probably knows, and that was coordinated by Jörg Kava of Atlas, and many people here in Breaking the Surface were involved in that, IFREMER, IST, and others, Jacobs University, and so on. And so the idea is to have a robotic vehicle with time-varying configuration. I mean with time-varying mechanical and soft links. So basically, as we will see, you will have separate robots that can join themselves, constitute only one vehicle, and then separate again. And the links can be mechanical, rigid, elastic, and or soft, meaning you have links guaranteed by communications and control. And the result was Swamp. It's a vehicle that we have here in BTS. It is possible for you to see it and to have experience with it. It is a reliable and highly modular and reconfigurable lightweight ASV for working in areas in ultra-shallow water applications. And there is research and innovation in materials, propulsion, hydrodynamics and mechanical design, and communication and control. This is basically the work that Angelo Detti is carrying on in his PhD thesis in cooperation with the University of Genova, and Angelo is at all the effects the inventor of this vehicle. So in the next minutes I will provide you a short presentation of the vehicle, but if you are interested in details, especially regarding mechanical choices, hydrodynamics, please ask Angelo. The vehicle, we employed soft materials. So the hulls are made of polyethylene foam, and then it is a kind of sandwiches between two panels of high-density polyethylene. And it was completely designed by Angelo and built in our lab using the numeric control machine we have. And so you see some phases of the construction. It is made by some layers of polyethylene foam, and they are packed together. It is basically a sandwich. So you have two hulls, and the holes in the hulls are locations for cylinders containing propulsion, control, navigation sensing packages, batteries, and there is also space for payload. And one particular especially innovative part of the vehicle is given by propellers, by actuators, because they are pump-jet. Pump-jet is a quite new concept applied to small autonomous vehicles. And the idea is that you have a pump, basically, that collect water towards up, and then in a nozzle, and then the water fall down, and through a nozzle it is a kind of jet motor, but with a small interaction with the environment. And you can put, because to have horizontal thrust, you have a vertical motor, you can put it inside the hull. So if you look at the vehicle, it seems to have no motors. And the thrust is, the efficiency is almost equal to the efficiency that you can have using propellers, and it is at an angle of about 15 degrees with respect to the horizontal. And each of these thrusters was mounted in a cylinder with also an azimuth thruster. So we have azimuth propulsion. It is possible to orient the direction of the jet with another motor. So the resulting configuration, of course, all this, we bought the thruster and the electronics, but all the canister, all the mechanics of the pump jet was built with a small 3D printer in the lab, and we made some basic thrust test, and you can see the jet outside of the propulsor. This is in the tank, the small tank we have in the lab. Anyway, each of them has a force of 1.25 kilos. And the resulting vehicle has this particular architecture, as I mentioned before. We have two hulls, and each hull is foreseen to be a robot. So we have connections only for power. So we have a canister with batteries in the middle of the hull, then a small canister for power distribution to the canister with control electronics, GPS, and HRS, and in bow stern, two thrusters, two pump jets. And communications between all these canisters are made Wi-Fi. And the idea now, the vehicle was born 1 month ago, so we have electronics and Wi-Fi only for one hull, and Gabriele in the lab now is preparing also the electronics for the other hull. And the idea is to have two separate electronic control boxes, one on each of the two vehicles. They are mechanically connected, but it will be possible also to use them as separated robots and also to make experiments of distributed control. We are very interested in that, having mechanical connection between the two vehicles. And some information about the design of the vehicle. It is about 40 centimeters height of the hull, 1.25 meter long, 1.10 meter of width, and the vehicle is a maximum weight of 60 kilos and a buoyancy reserve of 120 kilos. So it has a very huge buoyancy reserve. And the thesis, PhD thesis of Angelo is made in cooperation with the Department of Electrical Electronics and Naval Architecture Department of the University of Genova. And so in that small towing tank, we could perform also model identification test in the towing tank, also in very shallow water, to demonstrate, to understand which are the interactions with the hull, between the hull and the bottom. And the vehicle was launched 1 month ago, basically, in the Genova harbor on August 30. And this, the first day, we took a small Dyneema cable because we had to check everything, but it worked and proved to be very reliable from the first day at sea. And of course, also SWAMP will be an infrastructure available in the third TNA call of human robots. In this case, we think to operate it, we can operate it in a Genova press channel. It is close to the new harbor, commercial harbor in Genova, but it is a quite protected area. Many of you already had experience there. And candidate topics, but not only limited to this, because it is also possible to apply for applications, for instance, in very shallow water and so on. Otherwise, due to the particular configuration of the vehicle, it is possible to make research on dynamic positioning, on navigation guidance and control of single USVs, or about cooperative navigation guidance and control of multiple vehicles. So we had an overview, a technical overview of what we made during last 3 years. But, okay, we have not to think only to technology. When you see you made a lot of technological development of research in robotics and so on, in my opinion, we have to stop and think. We have to try to enlarge our view and don't focus only on technology and only on robotics, because there are other aspects that can in some way interact and modify and guide what we are doing from the point of view of robotics research and technology development. In fact, of course, we had both Proteus and SWAMP being motivated, and they have been designed, developed with a path from operational needs to concept. And it was very simple, moving from one vehicle to the other. We have also some steps on. But at the basis of all of this, there were funding and projects, because without them, we couldn't do that. We developed SWAMP with the money, some money that remained from previous projects, from some of the projects that I mentioned before related to Proteus. So we have funding and projects, but when you deal with funding and projects, many times now, especially working with marine robotics, you have to face economic, legal, and social issues. For instance, in the project I mentioned before, in Matrac, we have legal issues related to operating AUVs in harbor. We have social issues related to what we can do to have citizens perceiving the port as an engine for eco-sustainable technological development, and not as a source of pollution, of chaotic traffic, and basically a separation between the city and the sea, as it happened many times, especially during the last 50 years, in many of our towns. And in Bluehouse, we have the economic aspect of defining new products and business model connected to the technological development that we are doing, and also the social aspects of eco-sustainable exploitation of coastal areas in a world where number of tourists is increasing, but we have to preserve these areas, being also able to allow people living there to use tourism as a resource to live. So, the topic of social acceptance of autonomous robots interacting with humans in their daily life is one, I think, of one of the key topics we have to face now. And on the other hand, we have technology bottlenecks. And one is related to the robot capability of working autonomously in a structured environment. And that means also in human-populated environment. This is the basic problem we have in robotics. We develop new robots, new control algorithms, and so on, but at the end, we face against this wall. And this, as pointed out, for instance, by the Robocom++ project, by the proposal of a European flagship on robotics, and so on, we need a new paradigm in robotics. There are these two aspects: social acceptance of autonomous robots interacting with humans, and new paradigm in robotics. From one aspect, we need citizen engagement in our research. From the other aspect, we need to open in some way to new ways of introducing in robotics AI and machine learning. But on the other hand, don't forget, we are talking about marine robotics. But if we put together these three balls, we have a new paradigm for designing research and innovation processes in marine robotics. The basic idea is to consider, and this was motivated for us also from some experience that we had with mini robots. We developed some mini robots, and that there was a kind of mock-up simulating polar environment, and kids in Festival of Sciences and many exhibitions could pilot this robot, having the idea of being in Svalbard, in front of a glacier. And when we made it, there were people all the time. When they could touch it, and in some way they familiarized with robotics. And the lesson we learned from that is that we have to include in the research projects dissemination and communication from the beginning. So in some way, leaving in the past the classical dissemination idea that as roboticians we have, that is, okay, when we have a result, we communicate that. No. The idea is to find ways to involve citizens in our research from the beginning, not having communication as something that is on a side, but having communication and dissemination inside the research process. So engagement of citizens in research and technology development process. And we made the first experiments when we discussed about that, and it was in the Festival of Communication, Festival of Knowledge, that is in Camogli, a small village close to Genova, last September 14, 15. And we had the robot moving in front of the crowded beach. And there we thought an experiment. And basically, we also introduced learning by imitation that is based on reservoir computing, but in that case, it is a very fast way of training. It is a structure of neural networks that allows a very fast training of the network, because basically you have the main neural network, the reservoir, that is, in this case, with feedback, but because the system that we are going to consider is a time-varying system with the dynamics, but all the weights of these reservoir nets are established once randomly. And then but they have the capability of mapping the input, of clusterizing them. It is something mysterious. Also, you know Cristiano Cervellera. He suggested that, and he was very surprised of how it worked in real environment. But they clusterize that, and then what you optimize is only the relations between the output. So the optimization of the network is a simple least square. You provide them the basic trajectories for learning, and in a few seconds, they provide the weights for right connections of the output, the trained network. So you don't need a lot of time for training the network as in deep learning. And so we have fast learning and low training cost. And we applied it to a basic experiment. The goal is crossing two boy doors in the same directions. The people coming there, they could pilot the vehicle, kids, citizens, and make this experiment with no training for people before of that. And we used 16 trajectories, the first 16 that who test that, but during 2 days we had about 90 people piloting the vehicle, and due to also very hot weather, we had 2 slots in the morning and late afternoon of 2 hours. So there was basically a continuous queue of people to go there to make the experiment, to participate to the experiment. The recurrent neural network was of 500 neurons, and we have some trajectories made by people. Some of them were very skilled on the left, but moving towards the right, you have people that were many less able to pilot the vehicle. But all of these trajectories were useful to train the system. And the result here are trajectories made by the system autonomously. What you see on the back in dotted lines are the trajectories that we used to train the system. And what is particularly interesting is in the mid-experiment, where the robot started from a point that was not explored before. But at the end, after doing something, where I am, at the end it was able to join the area that was explored by the training system, and all the times it was able to reach the goal. So we have a small video of what happened there. So it was the vehicle working in Camogli. Camogli is a very, very nice place, a small fisherman village in the Riviera. And the vehicle, as I mentioned before, worked in a very crowded area. And we had, you see some of the boys there. This is the starting line. And basically, this is a simulation. Before tested in simulation, and the system was, we were able to train the system, and then also at sea it was able to do that. This is what people had to do with the vehicle. And in a remote control with a joystick, basically we remember the commands given by the joystick, by people through the joystick, and the position and orientation of the vehicle. The training set was made by that. And working, yeah, we have probably, we are still in the remote control. Then there was imitation learning, so SWAMP can mimic human pilots and being able to reach the target. And it was something that surprised also ourselves, because it is one of the first experiments in having a real robot at sea, and also, as we discussed in last EMRA meeting, there are some concerns on how to teach robot, how to use machine learning and AI in real robots, not spending years to teach the robot something. And of course, as I said before, the many kids piloted the vehicles. You know some of them. And there were very funny results. The two bottoms were in Prague, with Angelo and Marco piloting the vehicle, with exciting results demonstrating how the structure is robust. And on the top you see how Fausto participated to the demonstration. And okay, this work basically involved, in one way or the other, all the people of the unit of Genova of the Institute of Marine Engineering. And Marco, Giorgio, Roberta, and Angelo are here. And so if you have questions about construction of the vehicle, aerodynamics, motors, applications in environment control, you can ask also directly them. And thank you very much for your attention.